Hello everyone, welcome to our presentation on intelligent energy and carbon management in 6G. This is the flow of today's presentation. We'll start with introduction, then we'll move on to the literature survey to see the context, then we'll define the research gap and our objectives. We will detail our proposed methodology and algorithm design, followed by a comparative analysis and simulation results. Finally, we will conclude with the future scope of the project. As we move beyond 5G, the 6G paradigm introduces revolutionary technologies like Terahertz communication and holographic MIMO. While this enables ultra-reliable low-latency communication, they exponentially increase the network's energy density. This creates a sustainability gap. Current market focuses only on energy efficiency, but efficiency is not sustainability if the energy source is dirty. Our research goal is to shift the optimization objective from simply minimizing energy to minimizing carbon. We propose a carbon-aware AI that synchronizes network activity with the availability of green energy on power grid. We analyze several key studies to understand the current landscape. Kumal, which was published in 2023, highlighted that the energy spike in radio access networks but offered no dynamic solution. Fernando and Lazurio in 2024 focused on saving energy in IoT devices but ignored the massive power consumption of the base station themselves. Ismail and Boya in 2022 proposed self-learning networks, but they relied on static thresholds that failed to handle the dynamic nature of 6G traffic. And finally, Iggy Tankler defined the concept of green AI, which supports our choice of using efficient algorithms like PPO. From this survey, we identified three critical research gaps. The first one of them being obviously static sleep modes. Current heuristics like sleep when load is under 50% are too slow because they cause packet drops and they cannot wake up fast enough for 6G's low latency. Carbon blindness optimization today looks only at kilowatt per hour, ignoring the time of the day. Saving energy at night when the grid is clean is less valuable than saving it at noon when the grid might be dirty or under heavy use. Traffic unpredictability. 6G traffic is highly volatile and cannot be predicted by standard fixed rule. So the objectives of our research are to address this gap. We developed a dynamic power scaling model that adapts 5G energy profiles to 6G constraints. To design a carbon-aware DRL PPO agent capable of sensing real-time grid intensity, to implement a hybrid PPO framework that decouples energy use from carbon emission, and finally to achieve an 80% reduction in carbon footprint while maintaining zero packet drops. So our proposed methodology focuses on three core models. First, Terahertz power scaling. We use real-world 5G traces but scale them up by a factor of 3.5 to account for high molecular absorption losses at Terahertz frequency. This number 3.5 has been derived from various research papers that we read and previous background research. Secondly, MMPP traffic modeling. Unlike static 4G or 5G patterns, 6G patterns are dynamic. We use a MMPP to simulate sudden spikes from the holographic applications. Third, carbon dynamics. A system ingests a real-time grid carbon intensity curve that fluctuates stochastically, simulating the variability of wind and solar energy. This is the flow diagram of our system. In the left, we can see that environment that collects data and it feeds into our PPO agent in the center. The data is fed as a state vector into our and executes an action, which in turn gives the reward to the agent. The agent has three actions: deep sleep, which works at 30 watts, eco mode at 1000 watts, and boost mode at 4000 watts for high network traffics. Finally, the system calculates a reward based on the carbon saved and the packet drops, which updates the agent learning capabilities. Here is the comparative analysis from some other traditional methods. The static sleep heuristic relies on fixed thresholds, which have low adaptability and high QoS risk. The standard DQN agents are carbon blind and have slow convergence. Our proposed PPO agent, however, is a fully carbon aware, highly adaptable to traffic bursts and offers fast convergence with low QoS risk. Now let's look at the results. The legacy max performance system generated over 1.1 million grams of carbon dioxide. In contrast, our proposed agent reduced this to 185,000 grams only. This presents a massive 84.5% reduction in carbon emissions. This agent achieved this by identifying green windows periods when the grid was clean and processing every task during those times. But did we sacrifice performance? The answer is no. While the static sleep baseline dropped 50.9 units of traffic due to slow wake-up times, a PPO agent maintains 0% package drop rate, matching the reliability of the always-on baseline. The agent effectively learned how to sprint when the energy was clean to clear data buffers and to rest when the grid was dirty. To conclude, this research demonstrates high-performance 6G networks that do not strictly require high carbon emissions. By integrating grid intelligence into our control loop, we successfully decouple energy use from environmental impact. Our hybrid DRL PPO framework offers variable path for the green 6G era, ensuring compliance with global net zero targets. Here are the key references used in the studies, including the work we have previously mentioned. Thank you for your attention.